Okay, so I want to talk a little bit more about frequencies. We're going to do the square pulse, and we're going to talk about shifts, time shifts, and then on Friday we're going to talk about derivatives and integrals, which is kind of cool. And you'll probably pick some of that up in recitation this week, but it's okay. It's okay if you get to it first in recitation. And then we'll be in pretty good shape. Once we deal with that, then we can actually start talking about filtering and about convolution, and then it really starts to get interesting. All right? I probably on Monday will circle back and talk a little bit about computer assignment 1, because computer assignment 1 actually included some pretty neat stuff in it that I want to make sure everybody gets, that you, believe it or not, now have the tools to really understand in some detail. All right? You ready? So, okay, so where we left on Monday, we were dealing with a rectangular pulse, and generally speaking, we said the pulse, why don't we write it like this? If I write my pulse like that, it's got a total area of A, right? The base is 2A, the height is big A over little 2A, and so you multiply them, you just get a total area of A. And we said the Fourier transform was a sinc function where this height is big A, and the first zero crossing is at pi over A in units of radians per second. Beautiful. And if I wanted it in hertz, thank you, divide by 2 pi, you get hertz. Okay? So, and we understand the general principle that as your square pulse gets wider, your frequency pulse gets smaller. Okay, it gets narrower. And our interpretation of that was that as your rectangular pulse gets wider, that means you need lower frequency cosines to fit it. Right? As this gets wider, you fit it with slower and slower cosines. All right? If you represent that same information in the frequency domain, that means you want lower frequency energy. You want all your energy at lower frequencies, which by definition is what happens when this thing gets more compressed. You're compressing all your energy into lower frequencies. Honestly, if you get like 3 things out of this entire semester, that concept is one of them. Okay, it's a valuable thing to know. All right, because it has ramifications for a lot of different things. All right, and it's not just with a square pulse. I can give you almost any pulse. I can give you a triangular pulse. I can give you a whatever pulse, and all of them have this property that if you make them wider in time, then generally speaking, their frequency content gets compressed. All right, now. I've been a little bit sloppy, and no one's called me out on this, which is fine. We've been a little bit sloppy in drawing this function. Okay, so I want to, and we've been sloppy because we've only been doing the magnitude, right? What we haven't been doing is the phase, and I want to talk about the phase because that's actually kind of important. So I decided instead of kind of fighting with MATLAB over this, let's kind of do it by hand. I think might go a little bit more smoothly. So I'm going to do some scratch paper over here, and then we'll kind of go back and mark up our main diagram. Okay, so let's let our square pulse be x of t. So let's say that x of t is in fact the same square pulse that you see over here. I'm just going to give it a name now. And we'll say that x of omega is its Fourier transform. So does anybody remember offhand what we calculated was the Fourier transform?
It was
big A
times the sine of a omega.
Sine of little a omega
Over a omega.
Oh, little a omega. Cool. And we derived that. And then I told you to get smart, and I say, well, you don't need to rederive it every time, right? If I give you any old square pulse, you just jump right to the answer. Now, Fourier transforms, by definition, are going to be complex. Is this complex?
No.
Is there any J's in there? No, A is an area. This area is real. Sine of A omega is real. Little a omega is real. So this whole expression is, this is all real, right? There's no j's in there. Why is it real?
Because it's an even function. Even function.
Exactly. The way I've drawn it, x of t is an even function. Okay? As long as any, not just your square pulse, but as long as any x of t is even, then by definition, x of omega will always be purely real. Okay? That's fine. But we're still going to do good practice. I said because in general we're going to expect complex answers. We always do a magnitude plot and a phase plot. So what have I drawn here? I've drawn the magnitude. This plot is technically the magnitude of x of omega. You know what I'm going to do on my scratch paper, since I can? Because this is a special case where this is purely real, I can actually just plot this versus omega, right? I mean, I can just, a real function, I can always just say, let's just plot not the magnitude, not the phase. I can just, in this particular case, because it's real, I can plot the I can just plot the entire function, right? And if I plot it, what it winds up looking like is that. Now I got to make it symmetric. Is that symmetric? It's not bad. All right. Oh yeah. Okay, good. So this is the. So there's our old friend pi over a. Okay. So of course, if we take the magnitude of that, we're going to get the plot that you already see over there in the middle board, right? And if you take magnitude is just absolute value for real numbers. So there you go. We got absolute values. I'm digging it. So this plot makes sense to me. I like this plot. I'll put a check mark under it. Now, what I need, the plot that we don't have, is the phase angle of x of omega. And that, my friends, is where you're going to help me.
Well, if it's purely real,
Yes.
then the phase plot has to be either 0 or pi over 2. Or any multiple.
No, isn't it negative
Pi, 0, pi.
Yes. Remember, so the statement was, if you think about your complex plane, if your numbers are purely real, their phase angle is either going to be 0, or the only other place you can be on this plane to have a purely real number is over here on this axis. So your phase angle is either 0 or pi. Or any multiple. The multiples all mean the same thing, right? Okay, so pi, the one I will allow for also is negative pi. Right? And that's the same angle, right? Pi and negative pi is the same thing. Okay? So, tell me, right up here, what is the phase angle of x? Absolutely, right? I've got some positive number, right? A. Okay, what's the phase angle of A? If I express A as a complex number, it's really A e to the j 0, which makes sense. 0, right? It's just a positive real number. So here my phase angle is 0. What's my phase angle here?
0.
And here? 0. So as long as x of omega is a positive number, a positive real, my phase angle is 0. So here's minus pi over a. Here's pi over a. And between minus pi over a and pi over a, my phase angle is, what did we just say? It was 0, right? So whoop, there's your 0. This is easy, right? Even I can do this. All right. Now let's focus on the phase angle of x of omega in this interval between pi over a and 2 pi over a. Now what am I going to have? Right. I've got essentially, now I've got negative real numbers. And we've just argued that a negative real number has a phase angle. You could either say pi or negative pi. Either one, it's the same thing. Okay. So for example, if this number was negative 1/2, I don't know if it is, but let's just say it was negative 1/2. Well, negative 1/2 is really the same as 1/2 e to the j pi. Or 1/2 e to the j minus pi. It's the same thing. Okay, so let's just say pi. So between pi over a and 2 pi over a, I'm going to have a phase angle of pi. That's all right. Okay, between 2 pi over a and 3 pi over a. So what's my phase angle here? It's the constant 0. And here my phase angle? Pi, and then 0, and then pi. It's almost like there's a pattern, isn't there? Okay. So 2 pi, 0, so 0. You've got mail. 4 pi over a. Okay, so on and so forth. Sweet. Let's go back the other direction now. Let's do the negative frequencies. Hold on. I heard two things. You go first.
All right, since you have an
and then I'll get you.
function, x of omega, shouldn't you have an even phase plot?
No.
So the aperiodic function of the square root is just going to create a periodic function of the square root in the frequency domain?
But only in the you're only talking about the phase, yeah. Don't read too much into that. That's just a byproduct. That's just the phase. What property? Okay. What property do magnitude plots always have?
Always positive.
Well, always positive.
They're always even.
Right. Magnitude plots are always even. And your phase plot is always odd. That doesn't have anything to do with whether the underlying signal is even or odd, okay? Basically, as long as x of t is real, believe it or not, you can take the Fourier transform of non-real functions. You can take the Fourier transform of a complex function. It's ugly, but it's doable, right? But we're not dealing with that. As long as x of t is real, it's true that your magnitude plot will always be even and your phase plot will always be odd. So tell me, just on the argument of odd symmetry, what should my phase plot be between minus pi over a and minus 2 pi over a? Should be negative pi. Should it not? Isn't that how odd symmetry works? Is that right? Is it true that the phase angle is negative pi? Let's come and read it over here. So right now we're talking about the phase angle on this part of my function. What's the phase angle there? Right. I mean, it could be pi, because it's a negative real number. But it could also be negative pi, right? Pi or negative pi, it's the same thing. And since we're trying to get this odd symmetry, we'll say negative pi. Okay, and then it's at 0, negative pi, and so on. All right? Wow. What do you think?
Oh my God, symmetry.
Yeah, I know. What are you going to do? Okay. So this is pretty straightforward, okay? In the sense, I don't mean to discount if you find this complicated. It's okay if you find it complicated, but when I say it's straightforward, I mean that I'm trying to give you like the clearest cut case, okay? So just to kind of, to summarize, we started with an x of t that was even. Okay, and as a result of it being even, x of omega was purely real. Okay, which meant your phase angle either has to be 0 when x of omega is positive, or it had to be either pi or negative pi when x of omega was negative. And that's it. What do you think? You think nothing? That's good. I appreciate your honesty. Yes, sir.
Well, are we going to do the phase relationship also?
That phase relationship how?
Being that in this case it's odd, it's an odd function.
Well, phase is always odd.
Okay.
That's not just in this case.
But in general.
Always. Always, 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 your phase plot will be odd. Okay? So,
Well, if n approaches infinity, we're just going to get pulses at pi over every other
Yep.
pi over a.
yep. Because, as we've learned with Fourier transforms, you need all the frequencies in order to perfectly make your non-repeating aperiodic square pulse. Mathematically speaking, you need frequencies out to infinity. Okay? Now, let's do something different. We okay? So I'm going to do this problem one more time, and we're going to change something ever so slightly. I'm going to take my signal x of t, and I'm going to shift it to the right. You there? You with me? How far should we shift it to the right? Right, I mean, any shift will make it not even. Constant? Why don't we shift it by a? That's we don't have to shift it by a. We can really shift it by anything we want. But shifting it by a is going to give us the least, mathematically, is going to give us the least amount of ugly residue that we'll have to contend with. So I'm going to shift this by a. So all I got to do to shift this by a, so now my x-axis is there. This is going to be t equals 0. And this is going to be t equals 2a. So have I done anything other than shift this signal to the right? Can we agree on that? Just a time shift. So my question now is, what happens to the magnitude plot and to the phase plot? So we have a hypothesis. Okay, so first of all, now is x of t in its current state, is it even, is it odd, or is it neither?
Neither.
It is neither right now. Okay, it is not even and it is not odd. Therefore, in terms of x of omega, we expect a complex x of omega. It's going to have real part and an imaginary part. Okay. And I'm hearing a hypothesis that my magnitude plot should be exactly the same. Why? Because a time shift doesn't affect the frequency content, right? I still have all the same frequencies and all the same proportions. All the time shift does, at best, is affect how those frequencies line up with respect to 0. Yes, sir?
Why is it neither?
Why is this non-odd symmetry? Okay, so the definition of odd, where am I going to write? It's a good question. I appreciate you asking it, because I forget that that ties people up. Okay, so remember, even symmetry is defined mathematically as x of t equals x of negative t. And in terms of a plot, what that looks like is, something like that, where it's basically symmetric across the y-axis. So that's even symmetry. Odd symmetry is when x of negative t equals negative x of t. And in terms of a plot, what that looks like is it's sort of symmetric across, you've got to like flip it across the y-axis and then the x-axis. It's symmetric across the line y equals x, we say. Okay? So in other words, if this is x of t, and this is x of negative t, so x of negative t is the negative of x of t. That's odd symmetry. Now, look at what we have over there. Does it meet either of those symmetry conditions?
It doesn't repeat, so no.
It doesn't even need to repeat. It's the repeating has nothing to do with it, actually. Right? It's not symmetric across the y-axis, and it doesn't have this doubly symmetric property, so it's neither. Okay? Okay, good. So the argument was that the time shift, in theory, should not affect the magnitude plot, only the phase plot. So what I want to do is just explore that and make sure that that's actually true. So why don't we start with the formula? We'll write out the formula, and then we'll plot the formula and see if, in fact, the formula matches what we're expecting. So I think we talked about it in class, and I'm pretty sure it's in the book as well. Does anybody remember how the time shift property works?
Multiplied by exponential.
Right. So let's see if we can write the property down properly. So if x of t has the Fourier transform of x of omega, then x of t plus a shift has the Fourier transform of x of omega
Positive j omega tau.
okay, tau, whatever, t tau. Yes, that's correct. Okay, and there's a derivation for that, and the derivation is kind of cool, and sometimes if I can't remember if it's a plus or a minus, I just do the derivation. It takes about a second to do, and then I'm good to go. Basically, all you do is you say, if you have x of t plus tau, and you take its Fourier transform, right, isn't that the definition of the Fourier transform? Okay, you do a u substitution. You say u equals t plus big T. And if you do that, now you've got the integral of x of u, e to the minus j omega. Now you got to sub in for t. That gives me u minus big T du. And this becomes e to the minus j omega u times e to the j omega big T. And e to the j omega big T is a constant with respect to u, so that comes out. And what you're left with is e to the j omega big T times the integral of x of u e to the minus j omega u, which is in fact the Fourier transform. So that's it. Now I don't have to remember a formula. I can just, if I get lost, I can always find my way back by just doing this in the corner of my scratch paper. Okay, great. So how am I going to apply that concept to this problem? So I want to know, what is the Fourier transform for the square pulse that I have on the board?
Well, we have before and then multiply by e to the minus j omega a.
Good. So first of all, what's my time shift in this problem? What's my capital T? Minus a. What I've done is, if before I had x of t, now I've shifted it to the right by a units. So now I have x of t minus a. So according to the time shift property, what I should have is my old Fourier transform, same exact one that we just had, times e to the j omega capital T, where in this case my capital T is minus a. Okay. So let's plot that. I want magnitude and I want phase. Magnitude is the same thing. This is a complex number, right? Remember, complex numbers have magnitudes and they have phases. So when I talk about the magnitude, that hasn't changed. That's exactly the same as it was before. Exactly the same as it was before. Exactly the same. So this Doesn't change. This is still the magnitude plot of x of omega, as advertised, as expected, as predicted.
Actually, you can think of the original problem as being shifted by 0 degrees or 0.
Yeah, exactly. You can think of it as a problem with, right. If the original problem had 0 shift, then a would just be 0, and his e to the j omega 0 is 1, and that's it. That just disappears. Pretty sweet. Okay, now we have the headache of trying to deal with phase angle. So, I'm going to walk you through this. It's not hard, but you just have to keep track of all the pieces of this, okay? So, what is the phase angle? Remember, a generic complex number is m e to the j theta. So in theory, if you take everything that's in this exponent that's not the j, you should get the phase angle, right? So my phase angle for my complex exponential should be minus a omega. It's a line. Interesting. Very interesting. We're going to see that line in a minute. Okay. Now, and don't forget this plot, the sign, a sine a omega over a omega, doesn't that have its own phase as well? Right? It's either 0 or pi. We looked at that. That's the pre-existing phase. Right? So we'll say, why don't we call this has its own, that's the old phase with the one which we currently have plotted. So how does it work when you have two phase angles that are being multiplied together like this? What do you do?
Add them.
Right. Whenever you're multiplying complex number, phase angles always add. So basically, all I got to do to get my plot squared away is I've got to take my old theta, the one which you currently see plotted, and I'm going to add to that minus a omega. Got it? We're going to add minus a omega. So, in other words, I'm going to take this plot, and I'm going to add to it minus a omega. Let me make a quick plot of minus a omega. What's that going to look like?
Sawtooth.
Why a sawtooth?
Well, after you multiply with that one,
Right, but first I don't want to do the sawtooth yet. I just want to do minus a omega first.
it's just gonna go
Yeah, it's just a line with a slope of negative a. Exactly. Right? I mean, what is this? With respect to an independent variable of omega, that's a line with 0 intercept. Right? 0 y-intercept and a slope of negative a. All right, let me see if I can hit some of these points right. So I know my points of interest are pi over a, 2 pi over a, 3 pi over a, and so on. Okay, so at pi over a, at omega equals pi over a, what's my phase angle going to be? If I take omega equals pi over a and sub it in here for omega, be negative pi. Okay, so there's negative pi, 2 pi, 3 pi. So this plot is going to look a little bit like this. Oof. Okay, there's your, so this is your, what I'm now calling theta old. This is what I'm now calling minus a omega. Right, where we said that number was minus pi. And that number has to be minus 2 pi, and so on, in order to get the slope of minus a. And what am I going to do with this plot and this plot now? Got to add them together, because you're always going to add together phase plots. Anytime you multiply two complex expressions, you add the phases. Okay, so let's get our final plot. So this is the phase angle of x of omega. Okay, so let's start at 0. What do I have at 0? At 0, I've got 0 plus 0 is 0. Okay, even I can do that. That's in my skill set. Okay, in fact, it looks like as I progress all the way from 0, omega equals 0 to omega equals pi over a, I'm adding this line to 0. So that's pretty easy, right? I can do that. Boop. Okay, and this will be minus pi. All right, now what happens?
Shifts up pi.
Now, between pi over a and 2 pi over a, I'm going to take the same line, but now instead of adding 0 to it, I'm going to add pi. You there? So if I take this line and I add pi to it, it's now going to look like that. Is it not? I mean, I was here, I added pi to it, and that's it. That's my line again. Okay. That got me to 2 pi over a. Now how do I get from 2 pi over a to 3 pi over a? So now I'm here. I'm adding this line to, what am I adding it to? 0. Okay. So let's see. So now this is a line segment that goes from minus 2 pi to minus 3 pi. So let's see here. Minus 2 pi, minus 3 pi. So okay, and then it's going to jump up by pi again. Okay, and then down, and then so on and so forth. It's a mess, but it's there. Yes, sir?
Isn't your phrase positive there and negative there? And if you're adding them, shouldn't look different than you thought?
You're saying this is positive and this is negative?
Yeah.
Yeah, but this is only ever goes up to pi.
That's pi over that duration, isn't it?
I'm sorry?
It's pi over that like entire thing. No?
But between 3 pi and 4 pi.
I don't know. Continue with what you're saying. I'm sorry.
No. It's okay. I want to make sure you understand. Look, okay. So between 3 pi over a and 4 pi over a, this line goes from minus 3 pi to minus 4 pi.
Yeah.
And you're going to add to that pi. So when you sum that together, you get a line that goes from minus 2 pi to minus 3 pi.
Okay. I'm sorry.
Does that work? No, you don't have to be sorry. You have to ask. Okay, and that's what I drew, right? I think that's what I drew.
Why,
Yes.
why is it not going in consistent sawtooth? Why are we shifting it down at the negative 2 pi?
Well, I'm just adding pi. So first, it was this, right? You cool with that?
Yeah.
And then I added pi to this, so that jumped up by pi. Okay, so that got me up to here. But now, I'm at omega equals 2 pi over a. I'm adding this line segment to what? To 0. So there it is. I'm just adding that line segment to 0. What's the negative frequencies going to look like?
Going up, mirror image.
Mirror image, right? Not mirror, but I mean the odd symmetry of it.
No, you go up.
What do you think? Told you it wasn't pretty. Okay, I'm going to do one more thing and then we're going to call it a day. If I go to the computer, and did I get the symmetry right?
Yeah, it's supposed to go up after. I think you went. Down.
No, it's right.
Yeah, it's odd, so you gotta flip it
Yeah.
twice. Over. Okay.
Yeah, it's not pretty, but it's right. Okay, now, last question. If we go to a computer and have it plot the magnitude plot that we're looking at, it's not going to, the phase plot, it's actually not going to look like this. It's going to look close to this, but there's going to be one subtle difference. Okay? Not reverse.
It's going to constrain your phase angle between pi and negative pi.
Right. So, remember how we talked about real numbers and imaginary numbers? Okay. So we said that any number can have a phase angle going all the way up to pi or going back to negative pi. But over here I'm saying that we have a phase angle of 2 pi. What's a phase angle of 2 pi? Right, here's pi 2 pi. Isn't that the same as 0? Yeah. So basically, computers, when they do these calculations, they always constrain the phase angle to be between minus pi and pi. So even though numerically you can do it by hand and say, well, the answer is 2 pi or negative 2 pi, computer doesn't really make that subtlety, right? The computer basically just says, well, 2 pi is the same as 0. Negative 2 pi is the same as 0. So when you look at this at the computer, you're actually going to see something that's a little bit different. Not a lot different, but basically you're going to see let's see if we can sort this out in about 3 minutes. On Friday, we'll actually look at this in MATLAB. And remember I showed you that phase plot at the bottom of the screen on Friday, and it was like a total mess? And everybody, and I said, well, we'll get there. Okay, this is what it was. Okay, so, all right. So let's see. As long as omega is between minus pi and phase angles between minus pi and pi, we're fine. So this portion, that was okay. Okay, but now look at this. Over here, it's negative 2 pi. But negative 2 pi is really the same as 0. So instead of jumping it down to negative, so we went, oh no, we did this, and then we did this. We were okay up to here. Okay, now instead of jumping it down to minus 2 pi, where it's actually going to go is 0. Why? Because 0 and negative 2 pi are the same thing. And then it's going to drop down linearly till it gets to negative 3 pi. Negative 3 pi is the same as, right, so negative 3 pi is, let's see, negative 1 pi, negative 2 pi, negative 3 pi. It's really the same as negative pi. So your phase plot is going to wind up looking like that. It's the same thing. It tells you exactly the same information, right? It's not, I mean, both are equally correct, all right? They're telling you exactly the same thing. Because if I tell you the phase angle is 2 pi or I tell you the phase angle is 0, that's not just equivalent, it's exactly the same thing, right? There's no way of differentiating between that information. So this is, I would say, this is the same, but the one on the right is possibly more compact. Right? It's a more compact way of displaying the same knowledge. There's literally no difference between the two. All right? So here's why I'm showing you this. I'm showing you this because when I want to train you so that when you see this line here, okay, you look at that and you're like, oh, well, that's really just a line that keeps wrapping, okay? And a line that keeps wrapping around is basically, that's a constant phase shift. That's something like minus a omega, okay? And it's the slope of that line. The slope of that line is set by a, okay, which is set by the phase shift. So if this line is steeper, you had more phase shift. And if this line is less steep, you had less phase shift, or time shift in the original signal. If that line is steeper, that means you shifted your signal more. Right? We shifted our signal by A. We could have shifted it by 10A. Okay? If we shifted it by 10A, then instead of this line having a slope of negative a, it would have a slope of negative 10a. And it would go doink, 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 doink.
So what if you make it completely complex?
How do you mean?
All the way to j. I over 2, I mean.
Okay.
What you made?
I don't understand.
If you shift it to make it odd, just
Well, I can't ever shift that to make it odd. That plot will never be odd, no matter how much I shift it.
complex, fully complex.
Not that function. I can give you another function that is, but not that one. That was a lot. You did well today. Go home, read the notes, read your lecture notes. I get that this is a mouthful. The best thing you can do to prep for Friday is to work through all this again. Come with questions. Say, none of this made sense. Do it again. Or I didn't understand this part. Do it again. Okay, we'll regroup on Friday and try to try to iron it out. And we'll look at it on MATLAB and see what MATLAB says.
Could you have, does this apply to every function?